one hydrogen in the middle. Oh my gosh, I'm so bored. We draw a lot of structures in organic chemistry. There are several different structure drawing conventions that chemists use to depict the information that we need to communicate to the reader. The various drawing conventions have to weigh speed versus amount of information conveyed, and so we make some compromises along the way, and there's one structure drawing convention that we settle on as probably the most common structure drawing convention. The other thing is we can mix and match the structure drawing conventions depending on what exactly we're trying to convey to the user at any given time. To start, I want you to build a model. I want you to build a model of the molecule C4H10. Go ahead, physically pause the video right now and go build a model. If you don't have a model kit, I've got a link below that I'd like to use for the model kit that I recommend. So I mean it, really pause the video right now and see if you can build this model of C4H10. In fact, I'll tell you what, there's actually more than one C4H10 that you can build. See how many different unique C4H10 structures you can build. Okay, so there are two structures of C4H10 that you can build. Two unique structures, two unique ways you can arrange 4 carbons and 10 hydrogens. The two ways are the 4 carbons in a straight chain and 3 carbons in a chain with 1 more carbon sprouting off the central carbon. We're going to use these two structures to look at the various structure drawing conventions that we have in organic chemistry. The first structure drawing convention that we have in organic chemistry is just the molecular formula. The molecular formula, just C4H10. Now, this is the least descriptive of all of these structure drawing conventions because it doesn't really tell you how those atoms are connected. In fact, just by drawing C4H10, we actually described 2 completely unique molecules. So this is a way to describe molecules, to draw structures, but it's not a very good way. Another way that we can draw structures is the Lewis dot structure. Lewis dot structure may be the one you're most familiar with. It is nice for molecules that have less than 6 total atoms. For organic chemistry, though, it gets a little bit tedious. Let's take a look. I'll show you how. So for this straight chain molecule, we would have 4 carbons in a straight chain. Each carbon would then need a bond to all of its hydrogens. We would draw every single atom, every single bond, and every single lone pair if there were any lone pairs. These molecules don't happen to have any lone pairs. So for these 4 carbons, the carbon on the end has 3 hydrogens, and then 2 hydrogens, and 2 more hydrogens, and 3 more hydrogens. The structure on the right, we have the 3 carbons in the straight chain with 1 more carbon sprouting from the central carbon. There are 3 hydrogens on the carbon on the left, 1 hydrogen in the middle. Oh my gosh, I'm so bored. 3 hydrogens on top and 3 hydrogens on the right. I really don't care for Lewis dot structures very much. They're very tedious, they're very long to draw. They are perhaps the most descriptive, but they just take too long to draw. And these molecules have 3-dimensionality. You can see them as they're rotating here. There is a 3-dimensional depth to these molecules, and the Lewis dot structure does not do a good job representing the accurate 3D structure of the molecule. So what's next? The next way structure drawing convention is what we call condensed formula. Condensed formula is really good for drawing on writing the structures on a computer, or back before computers, typewriters. The condensed formula was the way we would do that. So the way we think about condensed formulas is we take the carbon atoms in a chain and we use them as the anchor points for the condensed formula. So we have our first carbon. Attached to that first carbon, there are 3 other hydrogens. So we write CH3. Then we move on to the next carbon. That carbon has 2 hydrogens attached, the next carbon has 2 hydrogens attached, and the final carbon has 3 hydrogens attached. With condensed formulas, we like to be efficient. If we see repeating units in a condensed formula, we like to combine them in a set of parentheses. I see 2 repeating CH2 units here, so we could alternatively write this condensed formula as CH3, and then in parentheses, CH2 for the 2 repeating CH2 units, and then the final CH3. For this structure on the right, we start with our first carbon. There's a carbon with 3 hydrogens attached. Now, the second carbon is interesting because it has the hydrogen and an entire branching group attached to it. How do we handle the branching groups? We let the reader know there's a branching group by encasing that branching group in parentheses. So we have the carbon and then the hydrogen, and then branching off of that is another CH3 group. The parenthesis says that this group is branching off the preceding carbon in the condensed formula. And then finally, our last CH3. Again, we like to combine repeating units in this structure. So I see that we have the 3 CH3 groups all attached to the central carbon. So we could write this as CH, this carbon would be this central carbon, and then 3 repeating CH3 units all attached to that one central carbon. This could be how we could write a condensed formula for this structure. The last, and by far the most common way we're going to draw structures in organic chemistry is the line angle structure. By far the most common, most convenient, most fast, most accurate way to draw structures in organic chemistry. The way we do this, watch what I do. This is really awesome. For this first structure, you ready? Ready? I don't know if you are. You ready? Done. This is the line angle structure for this molecule. How about for this other molecule? Okay, ready? Done. That conveys all the information that I need much faster, much quicker, much easier to draw. So we need to talk about some conventions here. Now, for all of these structure drawing conventions, I have separate videos that go into more detail. You can look at those links below. But for the line angle structure, what we need to recognize is that every vertex and every end of a line segment is assumed to be a carbon atom. So we can look at every end of a line segment. Those are 3 carbon atoms, and the one vertex makes up 4 carbon atoms. Every vertex, every end of a line segment is assumed to be a carbon atom. We also assume, we know that carbon makes 4 bonds, so we also assume that carbon has as many implicit hydrogens as it needs to get to 4 bonds. What do I mean by that? If you look at this carbon here, this end of a line segment is implied to be a carbon. There's one explicitly drawn bond to that other carbon. That means there must be 3 implicit hydrogens to get to 4 total atoms. This carbon here has 2 explicitly drawn bonds, so it must have 2 implied hydrogens. This carbon has 2 explicit bonds, so 2 hydrogens. This carbon has 1 explicit bond, so then 3 implied hydrogens attached to that carbon. Same thing over here. Each of these end of a line segment has 1 explicit bond, so there must be 3 implied hydrogens on each of these carbons. And the carbon in the middle has 3 explicitly drawn bonds, so it must have 1 implied hydrogen. And that matches with what we've seen above. These are the common structure drawing conventions in organic chemistry. By far, the line angle structure is the one that we need to get used to the most.
Thanks for joining us today, Ninjas. Be sure to watch these other videos to level up your Ninja training even more. As always, don't forget to like and subscribe.